Hello everyone. Today, I'm going to introduce our latest work RIOcc, a novel framework for 3D semantic occupancy prediction in autonomous driving. This work focuses on efficient cross-modal fusion and collaborative feature refinement, aiming to solve key challenges in multimodal 3D perception. Let's start with the motivation behind this research. First, let's understand why 3D semantic occupancy prediction matters. Unlike traditional 3D object detection, it focuses on the entire scene, including both objects and background details, providing richer environmental perception for autonomous driving tasks, like map construction and path planning. However, existing methods face three big challenges: high computational costs from processing large voxels, difficulty detecting occluded or distant targets, and inconsistent predictions due to the differences between LiDAR and camera data. Our RIOcc framework is designed to address these issues. To solve these challenges, we first changed the core data representation. Traditional methods like open occupancy rely on voxel features, which are computationally heavy. RIOcc, by contrast, uses bird's-eye view BEV features. As you can see, our framework has three key branches: a LiDAR branch with dual branch pooling, a camera branch with wavelet and semantic encoders, and an interaction branch with deformable dual attention. This design not only reduces computational complexity but also enables better feature alignment and fusion. RIOcc first processes LiDAR points and images separately in the LiDAR branch. LiDAR points are encoded into LiDAR features, which then go through multiple DBP modules to extract multi-scale features. In the camera branch, images are encoded into camera BEV features, refined by wavelet encoder and semantic encoder. The interaction branch employs deformable dual attention to enable cross-modal interaction between the processed LiDAR and camera features. After that, the fusion part, via BEV encoder and adaptive fusion, combines these features. Finally, the prediction module, using the occupancy head, generates the 3D semantic occupancy prediction. The LiDAR branch's job is to pull out high-quality geometric shapes and depth information from LiDAR data. To make this efficient and effective, we created a module called Dual Branch Pooling, or DBP for short. Here's how it works step by step. First, two components window detection and bottleneck ASP work together to widen the model's field of view. This lets it catch both global scene information and details at different scales. Next, DBP uses the separate attention branches that team up. The first one, channel-wise attention, picks out the most important data channels for understanding object categories. It does this by using max and average pooling to summarize spatial info. The second one, grid-wise attention, hones in on specific regions that matter for the scene's geometry, using 8-6 convolution to focus on those key spots. The final output from DBP brings together the best of both branches. It keeps all the useful geometric details we need while getting rid of unnecessary, redundant data. The camera branch extracts rich semantic and texture information, but camera data often has noise and inconsistencies. The wavelet encoder fixes this by decomposing features into low-frequency and high-frequency components, processing high-frequency data to reduce noise, then recombining via inverse wavelet transform for refined features. The semantic encoder uses a lightweight unit to capture both global and local semantic info, with an auxiliary semantic loss that boosts semantic consistency. Together, these two encoders make camera BEV features more reliable for fusion. The key to multimodal fusion is handling the differences between LiDAR and camera data. Our deformable dual attention, or DDA, does this perfectly. For LiDAR, we first encode the distance of each point to the sensor. This enhances distant features that are usually sparse. Then we aggregate local regions to get representative tokens. For cameras, we use self-attention to refine semantic tokens. Finally, deformable cross-attention lets the two modalities exchange complementary info. LiDAR's geometric depth enriches camera's depth and accuracies. In camera, semantics improve LiDAR's sparse regions. This bridges modality gaps and ensures consistent predictions. Now let's look at the results. RIOcc achieves state-of-the-art performance onto key datasets. On OCC3, D new scenes, we get 54.21毫升物, which is 4.82毫升物 higher than the previous leading method RIOcc. On new scenes occupancy, we reach 25.9毫升物, outperforming OCC Mamba and OCC Fusion. Importantly, RIOcc uses a smaller input resolution 256x704 and a lighter backbone RAISE-net 50, compared to many competitors, proving its efficiency without sacrificing accuracy. We present the visualization of RIOcc on OCC 3D new scenes without the camera mask. The results indicate that our RIOcc provides a more comprehensive prediction of the scene. It demonstrates improved detection performance for distant and occluded objects, along with a finer-grained occupancy prediction of the scene. To sum up, our RIOcc makes 3 key contributions: the balanced multimodal framework, a powerful DDA module for cross-modal fusion, and state-of-the-art results onto benchmark datasets. This work provides a new way to handle efficient multimodal 3D occupancy prediction, and we hope it inspires more research in autonomous driving perception. For future work, we plan to test RIOcc on larger datasets and optimize it for real-time on vehicle use. Thank you for listening.